Hello and welcome to the Edexcel Further Maths Mechanics 1 videos. This is the section on collisions in 2D, video 1.3, Successive Oblique Impacts with Plane Surfaces. So we're looking now at an oblique collision with a fixed smooth perpendicular plane. Even though the plane is fixed, we can still apply Newton's law of restitution, and that's going to be along the line that is perpendicular to the fixed plane here. What we're interested in is resolving the speeds and realizing that the speed parallel to the plane is unchanged at impact. So it's only the speed perpendicular to the plane that is affected by the collision. So if we have a ball of mass m projected towards a smooth plane like this, we can find the velocity after the impact by looking at the component parallel to the plane here, which remains unchanged, and perpendicular to the plane. After that impact, we can then think about another impact and what happens with that. And we treat each of these collisions separately in order to find out what the speed is and the velocity is after both impacts. This is collisions with smooth surfaces, and you can imagine this like looking down on a snooker table, and here's the ball rebounding off two of the sides of the snooker table. So if we think about these impacts, what would happen if both of them were perfectly elastic? So E, the coefficient of restitution, was 1. Well, that would mean that this final direction here would actually be parallel to the initial line of motion. So it'll be exactly the same direction, but in the opposite direction. Okay, so here let's look at this example. We've got a ball being projected towards two smooth planes. So it's going to hit this smooth plane first and then this one. And we want to find the final velocity after the second impact. Now it's useful to draw a diagram for each collision. And if we think about this first collision here, and the ball going off in this direction, or the mass. Okay, so what we're interested in finding is the component U1 in this direction and U2 in this direction, and then V2 and V1. Okay, so U2 we know is U cos 60 because it's adjacent, and U1 is U sine 60. Now the motion parallel to the plane is unchanged. That speed is unchanged by the impact. So V2 is also U cos 60, and V1 is U1 times E. So that's 1 over root 3 U sine 60. Okay, so now we're going to look at this impact here. You a little bit more obvious. So we're now going to hit here and come away in this direction. So we've got V1 along here and V2 along here, and then we're going to have W1 and W2. Okay, so W1 is unchanged because that is parallel to the plane now. So that is 1 over root 3 U sine 60. And W2 is going to be V2 multiplied by the coefficient of restitution here. So that's 1 over root 2 U cos 60. So when we work these out exactly, we get minus 0.5 U in the I direction. That's because we are traveling the opposite direction now to the initial line of motion, minus 0.35 the j direction because we're going this way and down instead of to the right and up. So now what we're going to try and find is the percentage change of the kinetic energy during the motion. So for that, we're going to need to know u, the initial speed, and v, the final speed. So u, fairly easy, it's just u. V is going to need to be the magnitude of our velocity vector. I've written this in exact form here so that I get an accurate answer for V. So V is going to be 0.5 squared plus 0.5 u squared plus root 2 over 4 u all squared, and that will be square rooted. So we end up getting root 3 over 8 u. So now we can look at the KE initially, which is a half mu squared, and then the final KE, which is a half v squared, so that's going to be 3 over 8 u squared. And we can see now when we compare these that the final kinetic energy is actually 3/8 of the initial kinetic energy, which means we've had a reduction here in kinetic energy by 5/8 of u squared, which is 62.5%. So we've had a loss of kinetic energy of 62.5%. Okay, thanks for watching. Next video will be 1.4, an oblique impact with a stationary sphere.